Hello everyone, dobar dan svima. Today I'm going to speak about multi-party computation beyond custody applications. My name is Dejan Radić. I'm a CTO of two companies. First one is ResolverSys, working with services orientation, and second one is Assister, startup aiming to improve data economy at the intersection of AI and cryptocurrencies. As we all know, there are a couple of privacy-enhancing technologies. MPC is one of them, and I hope today's presentation is going to show you that there are some other use cases apart from custody applications with the usage of MPC. So to start, we all know that the data is the new gold. We are utilizing data on a daily basis to do any kind of calculations. We are trying to actually achieve a lot of things by actually analyzing data. But what is the data value if the data is not processed? So what's the value if we don't do the processing of the data? Basically, there is no value. So any kind of analytics requires us to do some kind of processing, and in order to do processing, we need to see that data. But if everybody keeps their data, then basically nobody benefits, because we aren't enabled to do the analytics and computation based on that data. On the other hand, if everybody is giving their data, that means data doesn't have value, because everybody can easily do calculations, and there is no benefit for people who are actually creating the data and who are holding that data in order to generate any kind of value based on it. So what can we do there in order to enable people to do the calculation on one side, but also not to reveal their data on the other? And that's where MPC comes into play. So it enables us to actually calculate some results based on data from multi-parties without actually revealing that data. So when we go into like straight definition of this technique or protocol or technology in general, basically MPC is a protocol for data processing while not disclosing the underlying data. It enables the collaborative computation of multiple parties where end results ends at certain designated location where we define it. And there are a couple of things what we can do right now with multi-party computation, and those are arithmetic and logic operations, comparison statistics, and lately there are some advancements with LLMs and text where we can do computations based on text. So it's straightforward and simple. Everybody has its own data. We are calculating some function based on their data, but nobody is actually revealing that data. And we all know it's kind of a technology where, it seems we're doing some kind of sorcery there, but it's pretty simple, and next slides we're going to see some examples. We're going to see exactly how this works. So it all started in 1982 with Andrew Yao and his introduction of millionaires problem. So two millionaires, Alice and Bob, are sitting at a dinner, and basically they are competing who is richer. They don't want to reveal who is the richer one, but at the end, guy should pay. But, at some point they agreed that the richer one should pay, but they started playing this game, to determine it, but nobody wants to reveal it, So we're actually doing some kind of comparison operation of the underlying data that should be kept private. And Andrew started working on this problem, and it opened up a lot of research, and it exists for 40 years. So right now we have advancements in the crypto area, and since we are all attached to crypto in some kind of case, but in general sense, like Fireblocks with MPC CMP type of signing transactions, it's enabling us to do something that's called threshold signing. So we are doing multi-party computation to sign transactions. What does it mean? We're keeping private key at multiple locations. So basically you do partial signing with those locations, and by aggregating those partial signatures, you are getting the full signed transaction that can be relayed on the network and actually signed. So this is something we have. First research started at Coinbase, but has had too many cycles. Then basically Binance came with their own solution, and then Fireblocks managed to do it in a way that you have small amount of communication throughput, but on the other hand, maintaining the security that you are actually gaining by signing these transactions. So it looks like this. You have these keys, everybody signing the transaction, you have signatures. When you combine them, you get a signature that can be relayed on the network. But since our subject today is beyond custody applications, so what can we do with MPC apart from doing this? We all know that recently there has been a lot of talks and a lot of research about enabling data ownership in general. So when we talk about data ownership, we should think about data privacy. Because if we are enabled to keep the privacy of our data, and we have the ability to monetize that data, that means that we can have some kind of sustainable business model to gain any revenue on the data during longer period of time, not just immediately selling the data and we're done. Somebody copies it, posts it publicly online, and no revenue anymore. The thing is, how can we enable it? For example, mostly in Western Europe here, in the regional countries, everybody knows each other's salaries. But when you talk about, in general, in the Western Europe, salary is, pretty private topic. Nobody wants to reveal their salary. And then a couple of friends came together and they want to calculate the average salary. And Jane, John, Bobby, and Jack have different salaries and they know it, but how can we calculate the average without them revealing it? And one of the things that we can do is called additive secret sharing. So basically, those are the amounts, and we split those amounts into 4 figures. How? We should generate random numbers so that adding those 4 random numbers would end up with the salary. So we do it this way. For example, with 5,800, if you sum these numbers here, you would get 5,800. And same for the other salaries. Then basically every of these friends calculates these 4 numbers and have it for themselves. The next step they do is actually exchange the information about parts, everybody with everybody. John with Bobby, Bobby with John, and so on. Certain figures are mixed between each other. And at that point, every one of them has parts of the data of the others, but don't have understanding about their salary yet. They don't know anything. So that's straightforward. Then when you have partial data like this, you add these figures, everyone for each other, and then they sit together and say, okay, let's sum up all these figures. Still nobody understands each other's salaries, but we have a sum total of all of them. And when we divide it by 4, we get the average salary of all of them without actually revealing the underlying salary of each of them. So this is additive secret sharing, straightforward example how we can utilize it for any kind of statistical operation. Right now it's sum and average that we can use, straightforward. But what's the problem here? We've seen that everybody exchanges data with everybody, and we are creating a lot of communication throughput. So if those are friends talking at the desk, doing some kind of calculation on the paper, they're straightforward there, But if we come to the point of implementing this kind of solution and scaling it to a higher number of participants, basically we can come to the problem of full mesh communication, and that means that the amount of communication is raising with the square of participants. So similar like Metcalfe's law that says the value of the network is equal to the square of the amount of participants. So we have a lot of communication throughput. So is there some kind of way how to solve it, to reduce it, So on one side we are gaining this privacy momentum, on the other we are losing on throughput. So how can we do it? Basically, with everything, we've seen a peer-to-peer decentralized solution. oh, let's centralize it a bit. Let's see how it's going to work with a centralized identity in the middle called the moderator, and how it will look like. Every participant is generating one random number. And that random number can be, let's say, a number between -1,000 or -10,000 till 10,000. So some kind of range, symmetrical with like 0 in the middle. So there is some kind of, like plus-minus orientation with some kind of pseudo-random generator that they are having. They have their own salary, and they add this number to the salary. So basically, every one of the participants add this number to the salary, and at the end, when the moderator receives all these numbers, he calculates the average by just summing all the x's and dividing by n. Why? All the random numbers would cancel out, because if we have enough for participants, this n is big enough, all the pluses and minuses of random number generation would cancel out. And at the end, sum of all random numbers would be 0. Moderator wouldn't know any of the information about salaries of anybody, but at the end, he would be able to calculate the average. Why? Because sum of random numbers is approximately 0. For n large enough, it would be more probability that then it's 0 than it's not. So we won't have the fully precise answer, but if this random number generator is uniform enough, like it would be pretty straightforward solution regarding this. But then we come to a question, like, what if some party is dishonest? Like, what if somebody is lying about their salary? What if they want to present the final result of an average to look differently? And then we come to the question of verifiability. And that's one of the things where, we need to find ways how to make these parties, to be more honest and more straightforward. So verifiability comes to a couple of things. And one of them is interactive challenging with half results. For example, we could have the ability where you sum partially the data that you get from somebody else and communicate to the third side that can, for example, check the partial results between them. But that would add an extra communication complexity between them, for example. And what can be an issue there? If you get caught that you're cheating, they can exclude your calculation from the result. But what would be your real incentive to be honest in this case? For example, it can be something that we are utilizing within consensus mechanism with proof of stake. You stake some tokens, you show that you're going to be honest. We do interactive challenging game, and in the end, if we discover that somebody is not an honest player in the game, we just exclude him and take his money, So everybody would be honest, And one of the things that usually people use in these kinds of problems when they need to do something, you need to introduce some kind of trusted third party. So somebody who would be trusted that he has trust relations with everybody who is participating within the network. One of the things can be a reputation scheme. So if you have a mechanism to take or to influence the reputation of somebody else for being a dishonest player, apart from financial momentum he's doing from staking, that's kind of also a deal where you can get to the point of having these things. And people who are working with smart contract development know commitment schemes, so commit reveal patterns, where, for example, you can commit that something is the value that you should have communicated, for example, a hash value, but then in that case, you would be revealing it to somebody else afterwards. So, for example, checking party can be separate from, for example, calculating party. So, as you can see, there are many things you can do in communication with the crypto protocols where you can enhance the verifiability and have the honest players within the game. Similar with blockchain level and consensus mechanism and Byzantine fault tolerance that everybody is wanting to achieve within their L1 and L2 solutions. So, where do we apply this? we see data analysis as the first thing where we can apply it. But like financial, genomics, bidding, healthcare, those are all use cases where this concept can be applied for any kind of statistical operation, because right now there are circuits and there are options to do any kind of arithmetic operations like addition, division, multiplication, subtraction, and also logical operation like exclusive or, and so on. And also some kind of statistical operations that are based on arithmetic and logic operations. So anything that a CPU can do, basically multi-party can already do, but we don't have a full breakthroughs regarding multi-party computation on the level of tokens or words. But now with anonymization schemes of tokens and some other momentums recently happening, we are gaining momentum how these things can be used further. And now we're coming also to question, how can we combine it with other technologies? And now we talked about trusted third party. And for example, when you open up a website with HTTPS, you have something called SSL certificates in the background. Somebody is issuing those certificates. Those are trusted third party. And we're relying on something that's called public key infrastructure. And basically, somebody should connect your public key with your identity. And this is a trusted third party. For example, some issuance of certificates is always done through them. So for example, any kind of authentication regarding entering the network of multi-party computation can be used by PKI, and also signatures of some kind of calculations can be done using this concept. Symmetric encryption for inter-party confidentiality is always there. We should be able, to protect the confidentiality, but also, for example, with nonces to protect against replay attacks and so on. ZKP for correctness of computations. This is kind of way where you can, for example, utilize ZKPs, which is one of privacy-enhancing technologies as well as multi-party computation, to actually enable the prover verifier type of game, where at the end you would be able to verify if something is a correct information presented by somebody. Shamir secret sharing, which at the end enables multi-party computation, but only within a smaller number of participants. You can check it out. It enables you, for example, to split the private key into multiple parts, or split any kind of key, where you can have this threshold scheme where K out of N of participants can reconstruct the full key based on information they are having. And of course, homomorphic encryption, being able to calculate based on data that's really encrypted. So any kind of schemes combining all the cryptography knowledge that we are having and everything that we know about privacy-enhancing technologies can be applied all together in order to achieve this. But now people would ask, what about AI? And that's where federated learning comes to. Federated learning enables multiple parties to create a model without revealing their data, how they can do it. For example, we can have some kind of centralized party that's going to do aggregation. We can again call it a moderator. Moderator creates a model like, let's say, neural network with a couple of layers with the random data. So random weights inside of this network. And he takes this model and gives it to people participating in this computation. They use their data to train the random model so that it works with their data. Then, for example, they take all the trained models, send it to a moderator, and moderator does aggregation and update of the final model. That's one of the steps. The other can be he sends to the one, he does updating of everything, sends to the other, and so on, until finally we get a final model. We have trained data based on some kind of, let's say, underlying data that's private. We gain a model. Everybody can use a model, but we don't understand fully the underlying data. Of course, there are ways, and most probably some of us are going to ask a question, is there a mechanism where we can do an inference by mimicking backpropagation training algorithms in order to get to the input data and so on? Well, that's kind of a thing where you need to take a risk. But for example, if everybody is benefiting from, like revealing something about your data, but then still, like the gain from everybody having all the information is something where we will have a massive, like momentum. Banks are using this concept between each other. Banks aren't trusting each other, aren't trusting anybody, especially people who are depositing money to them. But, they don't trust each other. On one hand, they won't reveal anything about their transactions. On the other hand, the states are regulating anti-money laundering schemes, that banks should have any kind of momentum regarding this. So how to create a model which is going to give classification like money laundering, not money laundering, some kind of classification algorithm that's based on some kind of neural network model on one side, but also you have multiple banks that have their own underlying label data towards this. So the answer is federated learning. So straightforward thing that can be used on a daily basis, and we have proof of concepts you can check online that are working in this way. So for conclusion, basically, we have a new momentum right now, and we've seen also with the plurality event happening yesterday and the talks happening this morning, where privacy of the data is becoming a thing. People are starting to care about their data, about the privacy, and about putting data to the public, and what kind of conclusions can somebody else based on the contextual data make while having some kind of additional information about you, about your company, about your family, and so on. So right now, these kind of questions are raising. On the other hand, we have a couple of other momentums, really good mechanisms towards analytics of the data based on multiple sources. Even with the AI techniques, LLMs, and everything happening right now, we're really doing it in a really good way right now, also concerning non-structured data. So we're gaining momentum on that side. On the other, we have a momentum that's there in cryptography for quite a while, for a decade, and that's quantum computing. So there are a lot of algorithms in cryptography that needs to be disrupted, by having any kind of change regarding, algorithms that are working in a quantum era. So multi-party computation being a technology that's enabling us to, do privacy-preserving computation in a post-quantum way, let's call it like that, is a really good technology. And basically, as we can see, everybody knows about Fireblocks, but also on the other hand, we have the ability to calculate based on data that's private. And we have associated technologies that are enabling us to do it. And basically, we have the ability to collaboratively communicate and calculate some kind of function while keeping data private. And by combining arithmetic and logic operations, we can do statistical analytics. And we have the mechanisms to deal with dishonest parties and to verify somebody is an honest player in the game we are playing or not. And at the end, fully, if you look at it from engineering standpoint, you're always getting something on one side and losing something on the other. So it's always a trade-off. In this case, we've seen we sacrifice the decentralization on one side, precision of the result, in order to gain on throughput side. If we want more verifiability and ability to detect dishonest players, we need to have more throughput. But then still less decentralized and do it in a way that's less precise, but then we're going to gain on that side. And as with, for example, blockchain trilemma or any kind of other mechanisms where you're choosing 2 out of 3 and stuff, it's similar with multi-party computation. None of the technologies is perfect in every possible aspect. You're gaining on one side and losing on the other, and that's it. And at the end, for all the crypto guys and all the Web3 guys, what about data ownership? Can we enable the data ownership by doing any kind of tokenization right now regarding, let's say, incentivizing the people who are creating the data in a way that they keep it private but also have revenue based on some kind of data that they have produced it. And at the end, if like supremum, or like I would say that the final thing regarding data analytics that we are having right now is tied to AI/ML. Like how can we do or utilize this technology in order to have like any kind of computation within the AI/ML use case, but still, like having the ability to protect the underlying privacy. It's a model creation through federated learning. That would be it for today. We have 4 minutes for questions.
Hello, very nice presentation. And I have a question about the federated learning, and how do you exactly assess if somebody could be potentially like a malicious party which submits like the wrong weights to the model and basically tries to slow down the learning?
Well, as we talked, like any kind of way of doing it, either through zero knowledge proofs that he proves that he is doing the underlying stuff in an honest way, or by doing this kind of challenging. For example, send us partial information and then send us final information in total, and we're going to see if everything adds up. For example, he can send us some kind of aggregated results, which we can cross-check with the statistics, for example, of other participants. And if we see the underlying, like miscommunication regarding some kind of figures like variance, like any kind of like analytics on a statistical side, where we see mismatches, we can determine that somebody is dishonest. But fully to determine if somebody has been pinpointing some particular information within the data set, to exactly change it not to look like that, or doing some kind of outlier changes in order, for example, to reduce the variance, or like any kind of statistical operation by averaging or something, there is no easy way to actually do it.
Yeah, because like they could have basically like not a really good data set or something, and that could also be the case.
Well, like then we come to the point of trust. Like for example, with the communication with banks, like they would like to utilize it from somebody else. But then if they are the ones who are doing this model creation after somebody else, that's also kind of a problem where it's hard for you to determine if you get the information back and somebody has trained something after that. It's really hard to determine what parts of the data were changed based on your information, based on somebody's information. So, like there are ways where somebody can do these inference techniques in order to determine this stuff, but still it's a developing thing where dishonesty is a thing where you're either going to lose on the throughput side or on performance side regarding ZKPs.
Thank you.
First one is, what is the smallest size of group that you can determine that they have the necessary funds, for example? A second one, last time when we worked together, you told me that random numbers are no-no in our business. So how do you think to achieve that?
Really good. First question, actually in additive secret sharing is 3 of them. And in the example with the moderator, well, like most probably, let's say 50 of them, something like that. Because if you generate like 50 random numbers with uniform distribution that's symmetric around 0, like how much would you do it? For example, you can reduce it. You can say minus 100 till 100. You can have a smaller amount of participants on one side, and then this influence of the final result would be smaller, but everybody communicating, moderator would know in plus minus 100 euros the salary. So like if you reduce the amount of participants, you should reduce the range of the calculation of the random number. And regarding random numbers, yes, right now we have pretty good breakthroughs there. We have cards that are post-quantumly generating random numbers based on some kind of hardware techniques, and they can be used or run within RS-232 or let's say PCI slots or something like that, where their amount of randomness, like is already pretty good. So, like it depends on the use case, but if you want to be post-quantum, you should be using these kinds of cards, and there are a couple of them on the market. Any more questions?
In terms of MPC being used on-chain, are there some applications where most of the calculation is done off-chain? Is it light enough that a lot of it can be done on-chain? What do things look like currently? I'm not aware.
Well, there are a couple of projects actually aiming towards doing calculations on-chain. We know, for example, if you go smart contract-wise and like gas-wise communication on-chain is pretty expensive. And we are having a lot of, let's say, cheap calculations, additions, let's say, or any kind of arithmetic operations that are done on integers, for example, or something like that, where if we do these kinds of calculations on-chain, it can be done, but it's about the scaling out. And scaling out is still a thing where this technology is lagging. So usually how you would do it is, like have kinds of mechanisms of having results on chain and having registration of participants on chain and having these stakings or incentivizations over tokenizations on chain and doing the calculations off chain. But what can we do also is say, like as some projects are doing, Node is doing calculations. One protocol is a blockchain consensus protocol. The other protocol is MPC protocol doing peer-to-peer. So this kind of concept is actually there. Time's running out. Thank you very much. And